Good evening and welcome to tonight's lecture. I'm Ruth Brito. I'm from the School of Mathematics here in Trinity College Dublin. And first, a general announcement. This talk is being recorded and will be put online. So please silence your mobile phones and other devices. And also, please be aware that the question and answer session will also be included in the audio recording. This talk is being made possible in connection with a conference that we're running here this week called Amplitudes, or Amplitudes 2019, in which we study certain aspects of fundamental physics related to particle scattering. It's a field in which our speaker, Lance Dixon, has laid many of the crucial foundations that make current activity possible. He gave a research talk in the conference on Tuesday, in which very characteristically he presented some extremely tough computations done with a lot of effort, but with clear implications for observable physics and some really new deep ideas. He has been a leader in this field for 3 decades in work which was recognized by the Sakurai Prize of the American Physical Society in 2014. He's also been fortunate enough to spend most of his career in his native California. He got his undergraduate degree from Caltech, then did go elsewhere and received a doctorate in Princeton, during which time he made some seminal contributions to superstring theory. Soon after that, he found himself quite in demand as a lecturer. Shortly, then he was settled at SLAC, where he still is, which was then known as the Stanford Linear Accelerator Center. He started working on scattering topics. SLAC has also been the site of major discoveries in particle physics. And lately, this comes at the close of a series of visiting positions in Europe. And at the close of this week, he will be heading back to California, where, when he's not hard at work, you might find him cycling at top speed around the hills of Northern California. So we're very happy to have him here on his very first visit to Ireland. We're fortunate that he accepted our invitation to speak tonight. So, ladies and gentlemen, please give a very warm welcome to Professor Lance Dixon.
Thank you very much, Ruth, for that kind introduction. Can everybody back there hear me okay? All right, great. Well, happy 4th of July. Oh, wait a second, wrong country. But I promise there are going to be some fireworks in store because the 4th of July is actually a date that many physicists celebrate around the world, not just in the United States. And I want to tell you about some of the reason why and a certain quest that people in our field have been on for like half a century or so. And it's a quest that will take us to the innermost workings of the atom, but it'll also take us around the world to some of the facilities that where a lot of this work has been done. The meeting that Ruth referred to has been an excellent meeting, and they've done a terrific job organizing it. And it's been a meeting of theoretical physicists, mostly, who try to understand how different scattering processes work in a theoretical sense. I'm going to give you a journey which will have theoretical aspects to it as well, but I also want to tell you something about experiments and how experiments are done and how we learn the things we learn about the way the universe works. So why don't we get started? So our quest in this field is to try to understand the laws. Not the laws of humans, but the laws of nature. What are the things that tell us how the universe works? And of course, inside the universe, there's a whole lot of matter, and it obeys certain laws as well. For example, inside the galaxy, there's the Earth. There's other stuff at smaller scales, which I've been getting introduced to recently. There's even smaller things like ants and bacteria. And then there's the atom. And one of the amazing things is that when we look out into the universe, it's all made of the same stuff, almost. That is, all the stars that make up all the that give us all the light that comes from all the galaxies as far back as we can see is made of the same atoms that we can study in the laboratory. And the more we can learn about the atoms and everything inside the atom, the more we can learn about the laws of the universe more generally. Now, this isn't completely true. There is some stuff out there called dark matter, which we haven't got our hands on in the laboratory. I'm not going to talk about it too much in this talk, but there is a lot more to learn. Richard Feynman, though, made this point about the most remarkable discovery in all of astronomy is that the stars are made of the same stuff. Now, he's not an astronomer, so maybe the astronomers might think they made other remarkable discoveries, but that's one take on it. Anyway, let's take a quick tour through a magnifying glass at this sugar cube here. It's about a centimeter on a side, but we're going to use a special magnifying glass that has a power 100 million. And when we look inside the hydrogen atoms inside the sugar cube, we can see that the atoms of hydrogen are not elementary. They're made up of smaller stuff. And we can see, in fact, that there's an electron orbiting around a proton in the nucleus. And all other atoms have a somewhat similar structure where they have electrons going around at a similar distance from a nucleus, which might have protons and neutrons inside it. And now we're going to make another journey in by a factor of another 100,000 inside the proton. And this proton turns out, and I'll explain this more in a little bit, it's made of smaller objects, and there are roughly 3 of them in here. Ones we call U, and D. And one of the things I want to address in this talk is, what are these things? How do we know they're there? What holds them inside? Can we knock them out? And what other kinds of subatomic particles are there, and how do we learn about them? And also, how might they help explain the structure of our universe, the laws that all the particles in it obey? So that's sort of a quick overview of where we're going to go tonight. And when we go into such a tiny area, this has been called the quantum realm, at least in the recent movie Ant-Man and the Wasp. And this is Ant-Man here, shrunk down to angstrom size, entering the quantum realm. Well, actually, it doesn't look anything like this, but whatever. In the real world, in order to take our portal to the quantum realm, we're going to go to Geneva, Switzerland, eventually. And in Geneva, there's a laboratory called CERN, which is over here. And scientists at CERN and some engineers dug a big tunnel, which is 27 kilometers around. And they put 4 portals to the quantum realm at these locations around the circle. CERN has done some other amazing things too. You may not realize it, but the World Wide Web was invented over here. And so I want to try to explain, why did people at CERN build this gigantic circular ring? What were they thinking? Why do you need such a big machine in order to go inside the atom to see such tiny things? We obviously can see things of a certain size with our own eyeballs. You can see your hand, your finger, down to the width of a human hair. But to go much smaller than that, you need better optics than your eye. You need a light microscope. Then you can see blood cells and bacteria. But there's a certain limit. You can't really see viruses very well with the light microscope. You can see those things only with more advanced microscopes. For example, there are electron microscopes that let you go quite a bit further down. And at SLAC, we have a giant X-ray microscope, and there are other ones around the world that let us go see things further down. So why is that we need to use different kinds of tools to see the tiniest things? Well, first let me just mention a few things about the light that's used in a light microscope. Light is a part of a broader phenomenon called electromagnetism. It includes things like the discharges when you have lightning, the magnetic fields that are governing the pattern of these iron filings near this magnet. It also has to do with radio waves, power lines that are being transmitted here, and of course light from a light bulb and so on. All these things are really manifestations of the same basic phenomenon, various versions of it, called electromagnetism. And when you have electromagnetic objects that oscillate back and forth, you get waves coming out. And those waves could be radio waves when you run the electrons up and down an antenna, or they could be produced in a little bit different way in a light bulb. And we call the particles that carry this light photons. But there's another thing. We are going to a quantum realm, and in this realm, the laws of quantum mechanics are very important, and they say that there's two aspects to particles, that they have a duality, that you can think of them as either particles or waves. This shows an example of what happens when you shine light through two slits that are very close to each other. You get this pattern emerging here of these fringes coming out at different wavelengths. You can actually do this with your fingers if you're careful. If you look closely through a slit, you can see that things aren't exactly smooth there. So you can see this. And what this is a manifestation of is a duality. So if you read this one way, it says that light is a wave. If you read it another way, it says that light is a particle. And we theorists, we're constantly having to go back and forth between reading things as particles and reading them as waves. And this happens all the time in the quantum realm. And here's a chart that shows more about electromagnetism. It shows all the different varieties of phenomena you've heard about, that they're all really part of the same thing, what we call the electromagnetic spectrum. And it's ordered on the right here are things that have very long wavelength, like radio waves. Radio waves can have a wavelength like this, meters. And then as you go to microwaves, they might be centimeters. And then infrared and light, now we're talking about things that are called microns, or 10 to the minus 6 meters, or shorter, and down to the nanometers. And beyond that comes ultraviolet light, X-rays, and gamma rays. And as we go down in wavelength, we can resolve things much better. Because if something is spread out and is a very long wave, it's very hard to see anything. Things become fuzzy at that wavelength. When you look through the light microscope, things become fuzzy around this size under a micron, under 10 to the minus 6 meters. Now, a very important thing was noticed by Max Planck around the 1900, and he realized that because of this quantum property, that light was also a particle, and particles have energy, that he could associate an energy with frequency and also with the inverse of the wavelength. And as you move in this direction, the photons, the particles of light, have more and more energy. And so in order to make light or gamma rays that are that allow us to see very small things like the size of the proton, we need to have very energetic particles. And the problem is that we don't have any photon accelerators. So we have no way of making very intense beams beyond X-rays. And so while you can make light microscopes, and in some cases X-ray microscopes, there is no way to use light to look at smaller distances. So we're really stuck, except we have another way to do it. We can use what we call charged particles, like electrons and protons. And in fact, Ireland had a very key role in this, because Ernest Walton, who was an undergrad here at Trinity College and later a professor here, he was working with John Cockcroft at the Rutherford lab, in the Cavendish lab in Cambridge, and they invented together an early form of a particle accelerator. So it was able to accelerate particles to an energy. It was as if they had a battery that had 100,000 to 1,000,000 volts. And they could accelerate particles to high energies because if they have charges and you put them in this field, they pick up a lot of energy from that. In fact, they got the Nobel Prize in 1951, which just shows, to quote another Dublin-born person, the importance of being earnest. Now, they were only able to get up to about 1,000,000 volts that way. Out in California, where I work now, a lab was built in the first half of the 1960s. And that lab used a different technology, a lot of radio frequency cavities. Think of it as a huge number of microwaves strung together. And they put the electrons down this microwave, and by the end of it, it reached 20 billion volts compared to the 1 million that you could do with this Cockcroft-Walton accelerator. I should say that the Cockcroft-Walton accelerators lived a long life. They have been used as injectors in other kinds of accelerators, not this one, but other ones around the world. And so they've played a very important role even after the 1930s. But at SLAC, with this electron accelerator, we were able to accelerate, SLAC was able to accelerate electrons up to 20 billion electron volts, which doesn't maybe mean that much to you, but it's high enough energy that you can peek inside the proton and see what it's made of. And so the first direct view of proton substructure was made in this building here called N Station A from the electrons that were accelerated down here, bent a little bit, and came into this building. There were a few other things that happened at SLAC. We had the first US website because we were closely connected to CERN. And also, well, I had an office over here for 20 years until I moved off the slide slightly. So now let's go inside that building at the end of the linear accelerator. And what happened there? That electron beam I showed you before, it was slammed into a target made out of liquid hydrogen. And a whole lot of junk came out. But the experimentalists at SLAC, they only looked at one thing. They looked to see where the electron came out. This other stuff was a lot more complicated, but they could try to devise a mechanism for ignoring all the other stuff and just looking at the electrons. And by analyzing them very carefully, they were able to deduce that something was hard. It's like if you throw a bowling ball down an alley and you have a curtain so you can't see what happens, but you see a pin fly out to the side very, very quickly. You know there's something hard inside there. If you didn't see anything come out, maybe it was because you were hitting jello instead. Well, at SLAC, they saw a large number of electrons coming out after very violent collisions, and they knew they had hit little marbles or something like that inside the proton. In fact, these hard objects inside the proton were anticipated in various ways by thinking about symmetries by a theoretical physicist named Murray Gell-Mann. So Murray Gell-Mann passed away just over a month ago, and he was a real giant of theoretical physics in the 1950s and 1960s. And he coined a name for these little things inside the proton that I just gave the label U and D. He called them quarks. And he was inspired by the Irish writer James Joyce, by the novel Finnegan's Wake. And there's a line in there, 3 quarks for muster mark. And Murray Gell-Mann had developed a theory that required 3 of these hard objects. And he liked to sound like he had read everything, including Finnegan's Wake. And he liked the sound of this. And so he called them quarks. I happened to be, as part of the European tour that Ruth mentioned earlier, I happened to be in Zurich, Switzerland. And that turns out to be Joyce's final resting place. So I got a picture of him in a characteristic pose there. So that's another connection to Ireland. By the way, around the same time, the same concept was developed by another theorist named George Zweig. And he invented the concept, but unfortunately he hadn't read Joyce, and he called them aces, and that name never caught on. So now we know that as the quark model. And now I'm going to switch gears slightly, and I'm going to tell you how we particle physicists think about forces. Now, forces can be viewed in different ways. You sometimes talk about electromagnetic field, and you might say if there's a field and you have a charged particle, it might move in some curved path because of force moving it. Or even simpler, you might have the force of gravity, which causes anything you throw up to come down. But we have a different way of thinking about it quantum mechanically. We think that the field, which in this case is the gravitational field, in this case or it could be an electromagnetic field, but the fields are always associated with particles. And so we can think of the forces as being carried by particles. In the case of electromagnetism, that particle is the photon. And so we think of electrons as coming together and bouncing off each other, maybe because they're both charged, and like charges repel in electromagnetism. But we can discuss that by exchanging a photon. And when we do that, we often use some diagrams that were invented by the same theorist I was quoting from earlier, Richard Feynman, and they're called Fineman Diagrams. And so Feynman's development, which was around 1947, earned him the Nobel Prize in 1965, and it's really a ubiquitous way for theorists to think about what is going on in collisions. So I'm going to draw a few of these, but basically, like in this one here, if we run time in this direction, it describes two electrons coming in and bouncing off each other through the influence of the electromagnetic field, but we represent that by this particle, the photon, that's associated with light. So that's one example of a Feynman diagram. And this force is the electromagnetic force, and it is very long range. You can see it in action in a tabletop physics experiment when you deflect or you have charged static electricity that pushes foils away from each other. And you know that this force is very long range. Photons, and that's associated with the fact that photons are extremely light. It's very easy to make them. We don't need any fancy particle accelerators for that. Now, there's another force that we know about called the weak interactions. And as we'll see, these weak interactions they actually are very similar in some ways to this photon. There are particles associated with them, but these weak interactions behave very differently, and it's mainly because the corresponding force carriers are extremely heavy. They were first made by humans around 1980. And that force is, as a consequence, extremely short range. You can't see it in any experiment unless you peer inside the nucleus, way inside the nucleus. The range is so short. So now I want to go back to that experiment that the experimentalists at SLAC did in the 1960s and look at it from a theorist's point of view. And what our interpretation of what they saw is that a proton came in and it collided with an electron. But the collision wasn't really direct. It was mediated by one of these photons, one of these force carriers of electromagnetism. And the photon, it only talks to particles that have charge, but the electron has an electric charge, hence the name electron. And these quarks, they also have charge. They have funny values of the charge, but they have electric charge. And when the electron comes in, if it has extremely high energy, like 20 billion volts worth of energy, it will strike this quark extremely hard. And it will strike it so hard that the quark forgets that it was stuck inside a proton. Inside the proton, it's actually being bound together. We're going to talk about this a little more later. And so you might think that it would be in a soup, and it wouldn't be possible to to think of it as a free particle, but if you hit it fast enough, it thinks it's free when it's being struck, and it also starts to emerge just like a free particle. Now, I'm going to come back to exactly what happens to it, but the fact that when you hit something hard enough, it doesn't really matter how it was embedded in this proton, that was very important, and you could see these quarks directly as a result of these very high energy experiments. Now, what happens to that quark? Well, we're going to use a trick to see what happened to the quark because it wasn't actually seen directly in the experiments at SLAC. Instead, other experiments were performed within about a decade that were of a different type. Instead of having the electron come in to ordinary matter, like hydrogen, to look at it, it was possible to make, in the laboratory, the antiparticles of electrons. These electrons have negative charges. Their antiparticles have positive charges, so we call them positrons. And they were first predicted by Dirac. And in some ways, a positron is very much like an electron moving backward in time. And if you see this diagram here, it looks almost exactly like the diagram we had here, where an electron came in and an electron goes out. Quark comes in, quark goes out. Except I've bent the lines around in a funny way. Well, I've told you now that I want you to read time going this way. When you read it this way, this electron moving backwards in time, we call it a positron. And when it comes together, we say that it annihilates. These two particles completely disappear from the game. For a brief instant, there's something we call a virtual photon, but that quickly disintegrates or decays into two quarks. And now we can go to the laboratory once we've made these kinds of collisions and see what happens when these quarks come out. So this was done in many different places. For example, it was done at CERN. It was actually done in the same ring that I showed you earlier before a certain machine called the LHC was there. There was another machine called LEP, and they were able to see these quarks. You don't see single particles, but you see sprays of particles coming out. And here you see two of them coming out, and we say with fairly high confidence that there's a quark coming out this way and an antiquark coming out this way. Over here, though, you see three things coming out. In that case, we have an interpretation that there's a quark and an antiquark and some third thing, and that third thing is the force carrier for another interaction called the strong interactions, the ones that hold the quarks into protons. So we have a picture where the protons have these hard things in them called quarks, and they're being bound together, so there's a force associated with that, and every force has a particle that goes with it. And the particle in this case is called the gluon. It's the force carrier of the strong interactions, and we draw it not with a wavy line, but with a curly line, not so different from this line because we think it's actually fairly similar to this photon. And so you make an electron and a positron come together and annihilate, and out comes a quark and an antiquark. But some of the time, a gluon can come out. Some of the time, it doesn't. It's a probabilistic thing because we're doing quantum mechanics. Nothing is determinate. There's just different probabilities for different things happening. But before these quarks and gluons get all the way out to the detectors, they do something funny. They sort of have strings stretching between them that tend to break, and they snap, and they create more particles out of nothing, seemingly. There's a lot of energy in there, and they use that energy to make large numbers of particles, shown here. But these particles don't come out randomly. They come out clustered into these jets. So at high energy machines, oftentimes we see large numbers of these sprays of particles called jets. And they are tracers of the particles inside the proton, the quarks, and also the particles that carry the force called gluons. And this is a very strange force, but it's not really entirely the subject of my talk tonight. But it has this feature that at very long distances, the quarks are not allowed to be free. They're confined. They have to find other quarks or gluons, and usually they find an antiquark. Some of the time they find 2 extra quarks, and they get bound together into other particles that are called hadrons, originally for the Greek word for heavy. So at short distances, these quarks and gluons seem like free particles, and we can see them sort of emerging free, but at longer distances, they give us these funny jets of particles. So this is all comes under the name of another force, this strong force. And this force, also some of the nomenclature came from Murray Gell-Mann, together with Harold Fritsch and Heinrich Leutwiler. They named this force carrier the gluon. And also they named some of the other attributes. Well, the gluon should have a charge, but you can't use charge because then you'll get confused with electric charge. So they called it color. It has nothing to do with the color that people who speak in English are talking about. It's some funny phrase that we use to describe the color. And in fact, the quarks also have something called flavor that tells us whether they're up quarks or down quarks. Again, nothing to do with the common English word flavor. So we have a habit of speaking in strange tongues sometimes. So this theory of the interactions of electrons and photons, when you combine it with quantum mechanics, is called quantum electrodynamics. And since they had come up with this label for color, then it was natural to call this new theory quantum chromodynamics, or QCD. So we have a very nice theory that describes now the structure of the nucleus of the atom, at least the proton. Neutrons have a similar structure. It's a very complicated theory to work with in practice, but we're learning. But now I have to present the results of my literary analysis that I did while preparing this talk. I went through Finnegan's Wake. Well, to tell you the truth, I searched on the word glue. That's about how far of Finnegan's Wake I got through. And I discovered that although the word quark only appears once in Finnegan's Wake, the word glue appears like 10 or 11 times, including such pivotal ancestors as the glues, the gravies, and like glue be through. So it's clear that Joyce was way ahead of his time. So I've told you a little bit about the types of particles that we have. But these particles, they have one other interesting attribute, which is that they, for the most part, spin like little tops. Now, of course, when you spin something macroscopic, it has something we call angular momentum. And that angular momentum is a very large number compared to the spin of these elementary particles. The spin of the elementary particles has a tiny, tiny number called Planck's constant, which I sort of glossed over earlier, multiplying some small number like 0 or a half or 1. And the spin, though, can be very important. For example, if you need to go to the doctors and get an MRI scan, that MRI scan depends critically on the fact that protons in your body have spin. There's a giant magnet that is used to precess the spins around in all the protons in this guy's head. And by doing a careful analysis of when they're spinning and applying some other tricks, you can get detailed maps here. So spin is very important. And what I want to show you now is all the particles we know for sure that exist, except one. And this is a nice chart because it lays out the different kinds of particles we know about. And I've told you about quite a few of them already. I've told you about the electron. That's the carrier of electric currents. And it has a spin of 1/2. And it has two friends called the muon and the tau. And together we call these leptons because the early ones were very light compared to the other guys, the hadrons that I mentioned earlier. And then they have certain ghostly particles called neutrinos over here that have no electric charge, and they're very ghostly because they only feel the weak interactions. Up here, we have 6 more particles of matter, and these are the quarks. And here we have the up quark and the down quark, and then there are some heavier quarks, and we give them whimsical names like charm, top, strange, and bottom. And they all are very, in some ways they're a lot like these guys. They also have spin 1/2, but they have this color which allows them to talk to gluons. In the center here, we have the 4 forces. Well, they're really only 3 forces. There's electromagnetism, that's carried by the photon, the strong force carried by the gluon, and then the W and Z bosons, which are the carriers of the weak force. So these particles are very heavy. This particle is extremely light. In fact, it's exactly massless. But these particles weigh 80 times what a proton weighs. So they're extremely heavy. And one of the big puzzles is, why are they so heavy? And a proposed solution to that puzzle was provided that involved another particle called the Higgs boson. And the Higgs boson is extremely unusual. It's the only one in this whole chart that has 0 spin. We call it a scalar, but it doesn't have a little arrow pointing out of it, unlike all the other ones. I forgot to mention the force carriers, they all have the same spin. They're all spin 1. So every time we look at the spin, we know that the particle spin tells us something about the job it's supposed to do. These guys are supposed to mediate forces of some kind between these guys. These guys out here, we call them matter. Now, they're not all really matter. Only up and down and electrons really appear within matter. But we kind of call them matter generically. But then there's the Higgs boson. What is this Higgs boson in the middle? Well, that's really going to be the subject of the rest of the remainder of the talk. The elusive Higgs boson is the last piece in a theory of matter that we've been developing over the last 55 years or so. And it was originally conceived in 1964, although experimentalists didn't really take it that seriously for a while. But around 1980, the first searches began for this particle called the Higgs boson. And the searches got underway more seriously in the 90s and the 2000s. And it took literally thousands of clever physicists working at increasingly powerful particle accelerators around the world to finally bring this beast to quarry. To be a little more concrete, the explanation for this origin of mass was given 55 years ago, and Peter Higgs was walking around in the Cairngorms of Scotland in 1964, which must be why I like to go hiking in the hills as well. But so he had this idea that required a new particle called the Higgs boson. However, just to be fair, there are many similar ideas percolating around at almost exactly the same time. And for this reason, the Higgs boson is sometimes known as the Anderson-Brout-Englert-Guralnik-Hagen-Higgs-Kibble boson. So I hope you'll forgive me if I don't use the long name after this minute. And these are not exactly in the same order here. This is Philip Anderson, Carl Hagen, Francois Englert, Jerry Guralnik, Peter Higgs, Robert Brout, and Kibble. So I mentioned here, this was an explanation for the, quote, origin of mass. What does that mean, the origin of mass? Well, first of all, what is mass? As you may know from first-year physics, mass is this parameter m that enters the relation F equals ma, which is Newton's law that says that the force is the mass times the acceleration. We like to divide both sides by the mass and say that the acceleration is the force divided by the mass. If you had no mass, everything would zip around basically at the speed of light. And so mass is the ability to have things move slowly in some ways. So the world without mass would be completely different. The The mass is what holds the electron in the atom and gives the atom a finite size, a very small size. If we didn't have any mass, then the electrons would basically zip around at the speed of light, and it would probably be impossible to build very complicated things like organic chemistry, iPhones, and even humans. So the world would be completely different. Let me just give you another look at that chart that I showed you before and lay it out slightly differently, because we often think of it as matter has been divided up into two categories. One is stable, everyday matter. Well, this neutrino isn't exactly everyday, but the up and down quarks inside the proton are, and the electron is. And then there are the heavier cousins. These heavier cousins, except for the first moments of the Big Bang, they've basically just been made in various particle accelerators around the world, maybe in other worlds too, we don't know. There are also force carriers, the four I showed before, and then the Higgs boson is the last missing piece. What is its job? In some sense, its job is to, first of all, explain the mass of the W and Z bosons. And it does quite a good job of doing that. We've tested various aspects of this quite extensively, and it works quite well. And the Higgs boson also accounts for the masses of these particles. I don't say explain, because if we look at the masses of these particles, we see a very bizarre set of numbers. And these numbers are in no way explained by the Higgs boson, but we can sort of account for them. Let me say just a couple more words about the weak force. The weak force you may have heard about in the guise of radioactivity. There are certain kinds of radioactivity called beta decay, which is due to the weak force. When a carbon-14 nucleus, that's what's used for radiocarbon dating, when it decays into nitrogen, and it gives off an electron and a neutrino. And inside this process, inside one of these protons or neutrons, there's a W boson that is mediating this force and decaying into an electron and a neutrino. But this decay takes extremely long, like 6,000 years, whereas most particle collisions are over in an instant. And the reason it's so slow has to do with the mass of the weak bosons. We can actually draw Fineman diagrams for the weak force, and they look almost exactly the same as the diagrams we were talking about for electromagnetism, but there's a giant difference which has to do with the mass of the W's and the Z's. As I mentioned briefly earlier, they're about 100 times heavier than the proton, and that really means that particles, their influence is extremely short, only about 1/100th of the proton radius, and this causes these processes to happen extremely slowly. And the weak force was a big mystery that Peter Higgs was trying to solve, and the other people working on that problem at the time. So I'm not going to give a very detailed explanation of how the Higgs boson accounts for it, but I want to draw a little analogy, which is that if we have particles that have electric charge, we can bend them in magnetic fields. And so we can say that, that the magnetic field is the origin of curvature. And what I mean by that is that if there's no magnetic field, it will just propagate in a straight line. The force will be zero. It won't be accelerated. But if there is a magnetic field, turns out it will go in a circle. And how much it's bent, how much it's curved, depends on how much it talks to the magnetic field. And we say that's the electric charge. So if it has zero charge, it will just keep going, no matter what the field. If it has electric charge E, it'll go in a circle this size. 2E, it'll curl up even tighter. And so the paths of these particles depend on the field. And of course, this has to do with how it interacts with photons, the quanta or the particles associated with light. Now, in the laboratory, we can change electric and magnetic fields very easily. So in some ways, the origin of mass is very analogous to this origin of curvature from magnetic fields. Instead, what we think is going on is that there's a Higgs field that permeates the entire universe. In contrast, and it sort of does the same thing. It alters the trajectories of particles that talk to it. Now, when we say the ones that talk to it, we give them a little coupling, say lambda. If the particle doesn't talk to the Higgs, then even when there's a Higgs field, it still moves at the speed of light. Just like this neutral particle here moves at the speed of light, even if there's a magnetic field. But if a particle talks to the Higgs, then it will slow down. It will move at a different velocity, less than the speed of light. It will have a mass. And the larger the mass, the more it talks to the Higgs, the larger the mass it will have. So that's what we call the Higgs field. It's something permeating the entire universe, and it's really locked in there. It takes too much energy to move it, unlike electromagnetic fields. And that field has always been turned on, at least since the first nanosecond of the Big Bang. So the Higgs actually does talk to many different particles in this model we have, the standard model, but it doesn't do so equally, and that's why it's so elusive. It talks to particles proportional to their mass. And the things that we can make accelerators accelerate are protons and electrons. And the things inside them, or the electron itself, happen to have very tiny masses. If we could make an accelerator out of top quarks, we would have no trouble making the Higgs. But the top quark lives for 10 to the minus 25 seconds or something, and so we're not going to be accelerating it. It just decays too fast. And similarly with all these other particles, possible exception of the muon. But because we're stuck with these particles, it's very hard to find the Higgs boson. But nevertheless, we have to try. It's the one last piece in this standard model. To make it, because it's a pretty heavy particle too, we need a lot of energy. Einstein told us that the amount of energy we need is proportional to the mass of the particle times the speed of light squared. And so we need very energetic particle accelerators. So finally that brings us back to CERN, to Geneva again, where the Large Hadron Collider was constructed over a period of about 10 years, and it started colliding in 2008, and it's anticipated to keep colliding into the 2030s. And it collides protons at a much higher energy. SLAC, remember, had electrons at 20 GeV, so this is almost 1,000 times more energetic protons. I forgot to mention, this is the Geneva airport for scale. So the runway of the Geneva airport would fit comfortably inside this machine. There are two detectors in particular that were designed to look for the Higgs boson, and they're called ATLAS and CMS, and they're located approximately diagonally across the ring. This line here is the border between Switzerland on this side and France on this side. I got to spend a year living inside the LHC ring, somewhere around here in France. Here's a picture when you go inside the tunnel. These are the Lhc Dipole Magnets. Pretty much the whole ring is filled with magnets. You need 27 kilometers worth of magnets in order to bend protons that are moving that fast around in a circle. And these magnets are a real work of art. They have a magnetic field of 8 Tesla. That's more than the field in an MRI, and it's 27 kilometers worth of it, 100,000 times the Earth field. And these magnets are chilled to just a couple degrees above absolute zero. At one of these collision points, these portals to the quantum realm, sits the ATLAS detector. This picture was taken before the inner part of the detector was filled up. So it just shows the outer part of the detector. And if you look carefully down there, there's a human for scale. That's a real human. This is the other detector in this game, the CMS detector. or a schematic of it. And you can see that it's incredibly detailed inside. It has a huge number of layers, and each of these layers has a different function. Each one is trying to extract a different kind of information from the particles that emerge from this collision in order to find the Higgs boson, as well as look for many other things. Here's another picture of CMS showing someone inspecting the inner part of the detector. These are enormous detectors. I forget how many tons they weigh, but at the same time, for example, in the very center of them, they have these small devices called pixel detectors that are designed to measure the tracks of particles at the micron level. And so this business of constructing detectors at these large accelerators is really a blend of shipbuilding and nanofabrication and microelectronics that is quite an incredible mix of disciplines. So this machine, the LHC, it's an incredible data fire hose. The experiments can't handle all the data that the LHC produces, not by a large margin. So they have to be extremely selective. This is a picture of one collision of two bunches of protons at the LHC. And it's not just one collision. It could be anywhere from 20 to 60 separate collisions happening at the same time. The experimentalists have to figure out which one of those is the interesting one and discard all the boring ones. And this happens 20 million times a second. And you cannot save those 20 million events. You can only save a few hundred events. So you have to think very carefully and very quickly about which events you want to save. So it's an incredible challenge of data, of acquiring the data and making these decisions extremely quickly. But at the end of the day, you can definitely discern things. For example, you can see that there are some tracks here that came all the way out. And because they're yellow, well, okay, they labeled them yellow, but you can see which is the interesting collision that produced them. So there are lots of handles, and the experimentalists are great at using them to the max. Now this is the theorist's picture of what happens in a collision at the Large Hadron Collider. And it doesn't look quite as simple as some of the other ones I showed you, because it's not. It's a real mess. Here are two protons coming in, and these three arrows depict the fact that they have three quarks inside them, but in fact they really have larger numbers of quarks and gluons. And all the action from our point of view is going on in this little piece here. At least this is the piece that we can help out with. This part out here, it's very complicated. There are ways to model it which are very useful, but it's extremely difficult. And this is the part that is most closely related to the kinds of things going on at this conference. So I say that we can calculate this in principle, and what I mean is that we can write down diagrams of the form that Fineman told us how to do, but these diagrams are not the simple ones I showed you before. For example, if we want to see what happens when two quarks annihilate inside the proton, produce one of these weak carriers, and 1, 2, or 3 gluons. For one gluon, at the leading order in the approximation, we need 2 graphs. And we need 2 of these Fineman diagrams. And then we start to need about 10 at the next order. But if we come down here to 3 gluons, we need dozens of graphs just to get the first crude approximation. And then we start to need hundreds or thousands of graphs. And so one of the things that we've been learning over the past few decades is that these Fineman diagrams are really great for getting intuition and so on, but for actually getting numbers out, sometimes they're not the best thing to do. And it's sort of like having a handful of sand grains on the beach. If you just have 1 or 2, it makes sense to think about each grain. But once you have a whole handful of them, the whole thing is like a fluid. It behaves very differently. And a lot of what has gone on to boil it down and oversimplify it completely in this field is to think about these amplitudes, the scattering of these particles in a totally different way. And as I mentioned, that's the connection to what's been going on here at Trinity College in the past week. let's return to the LHC. As of this date, July 4th, 2012, over 800 trillion proton-proton collisions had happened at the Large Hadron Collider, and fewer than 800 Higgs boson candidate events had been detected. But nevertheless, that was enough for a discovery, as we'll see in a second. Since that time, since those 7 years ago, there have been 30 times as many collisions taken place. So we've gotten a lot better view of the Higgs. But let's first say a couple more things about how we see the Higgs, this boson. As soon as it's produced, we know that it instantly decays. So we never see traces of it directly in the detector. And because it likes to talk to things that are heavy, it usually decays to heavy things, especially heavy quarks and sometimes gluons. It can also decay to W and Z particles, but they usually decay to quarks too. The problem is that when things go to quarks, they're almost impossible to see because the Large Hadron Collider is banging together bags of quarks and gluons, and they're just flying all over the place. And so it's almost impossible to see them. Here's just one of a zillion different events at the LHC that have many, many quarks and gluons coming out that emerge as these sprays of particles or jets. So you need to do something different. You need to look at things that happen very rarely but are very clean. And one of the best things to do is to look at the case where the Higgs boson decays into 2 photons. It's kind of ironic because the Higgs doesn't directly talk to the photons. But this is quantum mechanics, and in quantum mechanics, pretty much everything that is allowed by energy and momentum conservation can happen. And so the Higgs actually does talk to the photons through this very heavy quark I mentioned earlier, the top quark. And the Higgs can decay to 2 photons, but only 0.2% of the time. But that turns out to be enough. By the way, the Higgs is actually produced through one of these quantum processes too, through this same top quark, talking to the carriers of the strong force, the gluons. So we draw this diagram to remind us how we make the Higgs most of the time. And one of the ways we can actually see it by seeing 2 high-energy gamma rays come out of the detector. Once we see gamma rays, they may come from other sources, but we can actually see a bump associated with the mass of the Higgs boson if we look carefully. Now I'll show you a little movie here, which was made by CERN to show how the LHC operates. And this is after one of these linear accelerators. It goes into one storage ring, boosted up to 1.5 billion electron volts, then another one to go to 25 billion electron volts, then a third ring to go to 450 billion electron volts, then finally into the main ring to go all the way up to 7,000 GeV, 7 TeV. Here we're taking a look in the tunnel. That was the Lagrangian of the Standard Model for aficionados as graffiti on the wall. This is the French-Swiss border. They pass it 1 million times a second or something like that. Here's a view of a proton, the poor proton. It's about to meet its maker, or at least another proton. Here it comes. This is inside the Atlas detector. Time seems to slow down when you're on the precipice of eternity. The protons collide. A huge number of particles come out, but 2 of them are green. That's how we know they're photons. No, I'm just joking about it. So this was a snapshot of a Higgs particle being produced and decaying into 2 photons. But you have to collect huge numbers of these photon-photon events in order to deduce the existence of the Higgs. That was in Atlas, so for equal time I have to show a candidate from CMS, otherwise somebody would get mad. I should also mention that there is a second good way to see the Higgs, which involves decaying to 2 Z bosons, each of which goes to muons, or possibly electrons. So there you see 4 very characteristic charged tracks coming out. This one is very nice, it's just quite rare. And in July 4th, 2012, evidence was presented, or the discovery of the Higgs boson was announced based on plots like this, which show a whole lot of events with 2 photons coming out and a little bump in this curve, which was, however, statistically significant. And since it was the 4th of July, at least in the United States, there were a lot of fireworks. And so this was the culmination of like 50 years of searching. So a lot of us were pretty excited around the world. Here were some people who were particularly excited. They were at CERN at the time when the discovery was announced. So these were 2 of the lead experimentalists, the spokespersons of the experiments. This is Fabiola Gianotti, who is the spokesperson for ATLAS, and she is currently the head of CERN, the Director General. And this is Joan Candela from CMS. And Steve Myers was one of the lead accelerator physicists who made the LHC work. This was the Director General of CERN. And then some of the theorists got into the picture too. There was Jerry Guralnick, Carl Hagen, Francois Englert, and Peter Higgs. And then they also got their moment in the sun a couple of years later when they got the Nobel Prize for this. Unfortunately, the Nobel Prize can give to at most 3 recipients, but there were like over 10,000 people, involved in various aspects of this quest. It's a little bit ironic because some of the ideas that Higgs and collaborators came up with were actually used by Steven Weinberg and Abdus Salam and also Shelley Glashow in work that was awarded for the Nobel Prize way back in 1979. In this 1967 work by Weinberg, which was the best known, was actually still ignored until about 1972, when there was some seminal work by Gerard de Tooft and Tini Veltman, which built even more explicitly on Higgs's idea, and they got the Nobel Prize in 1999. But unfortunately, these other guys essentially predicted a particle, the Higgs boson, so they had to wait till the particle was discovered. And that's how it goes sometimes. So the question is it all over? Not quite, although we're getting close here. I just wanted to say that we still have incumbent on us the task of showing that this thing is the Higgs boson. It's not good enough to just say, yes, it was number 4, I'm positive. We need to have some way of distinguishing the thing that was found from other possibilities. One way to do that is to measure the particle's properties. In fact, the spin has been pretty well determined to be 0. So it looks like a scalar, it looks like a Higgs from that point of view. We also need to check how often it's produced and how often it decays with each kind of disguise, the different ways you can see it, and compare with expectations. But because we've had a chance to see a lot more Higgs bosons at the LHC, this has been done pretty well already. And this is probably a rather complicated plot to people who aren't used to this thing. But there's one target point in the middle, this star here. These are the predictions of the theory. And these shaded regions are what the experimental measurements are. And the reason why they're ovals and stuff is because of the uncertainties. These will shrink as the LHC runs longer. But already it's looking consistent with the standard model Higgs boson to within about 10%. So, but we still have this nagging feeling that there's something else going on. One quote is by Michael Turner, who said that the Higgs is like a plumber with duct tape, holding the standard model together. And maybe one sense of what he meant was that we have all of these different masses, and we basically explain them by putting in the same number of parameters. So that's what I meant by saying it doesn't really explain them. So because we have this nagging suspicion that something else is out there, we've made a lot of suggestions for what it might be. We just call it generically new physics. It might be a new symmetry or a new law of nature. It might be that space has more than 3 dimensions when you look inside at short distances. Maybe this Higgs particle isn't elementary, like protons. Maybe it's made up of something else. We have lots and lots of ideas, but we don't really have a firm guidepost. The LHC has been examining all of these, as many of these ideas as they can, and they've found nothing. So for the moment, we're stuck with the Higgs boson, although the LHC is going to run for quite a lot longer. Let me return very briefly to the universe. I'm not going to say very much about this because time's a wasting, but if you look at the universe in microwaves, this is what you see. You see, well, actually, if you don't look very carefully, you see an almost uniform glow. But if you look very carefully at the 10 to the minus 5 level, you see a huge number of hot and cold spots. And these hot and cold spots are actually very consistent with a certain theory of the way the universe was born. And in that theory, there's a scalar field. And that field is called the inflaton because it produces a phenomenon called inflation. So there seems to be very nice evidence that there are other scalar fields in the universe that actually played a key role at the very birth of the universe. But we have no idea how this inflaton is related to the Higgs boson. Some people think it could be the same particle. It's a bit controversial, though. But anyway, by studying this scalar in the laboratory, we may yet learn more about the way the universe began and where it's heading. So this hunt for the Higgs boson was very long and arduous, but you guys hung in there. I'm proud of you. We're still wondering if the solution of the origin of mass is really as simple as it was imagined almost 50 years ago. It's looking a little bit like that, but we still need to look more closely and go to higher precision at the LHC, possibly at future accelerators. And those of us who are theorists, we have jobs to do in trying to help the LHC distinguish all the different possibilities by making more firm predictions about what the standard model looks like at the LHC, as well as what new physics looks like. And overall, we also use some of the things that we do at this conference to try to understand better in other ways what makes the universe tick. So thanks a lot for bearing with me for an hour, and I hope you had a fun time. Don't be shy.
As someone who thinks back to maybe 20, 30 years ago, I mean, the big thing about the Higgs was that as a scalar field, it's fundamentally unstable, and the belief certainly was that something had to be found at the LHC. Has that been a disappointment?
So there was a sort of theorem that something should show up at the LHC. We had evidence from other sources about what the mass of the Higgs should be if there was nothing else out there. And there was a sort of theorem that if there was no Higgs, you would violate certain principles. But the thing, and so of course, in some ways, it's a relief that the Higgs was found, that we don't violate these other principles. But the unease that I was mentioning earlier is what has led, and it's a little more than unease. There are also certain ways of phrasing it more quantitatively, but it's something we call fine-tuning, that the theory looks unnatural if you can go and get to energies much higher than we can now. That's what we call a thought experiment or a Gedanken experiment. So there has been a lot of, most people would have bet that other things would have been found by now. So apparently, if the new physics is there, it's more subtle. We know there is new physics out there somewhere, we have dark matter, for example. I didn't talk about it at all, but we know that none of the particles in the Standard Model can be candidates for dark matter. So we need something else. There are many theories in which you could have produced dark matter at the Large Hadron Collider. What you would see is it leaving the detector, and it would make its presence felt by asymmetric looking events. So that's been looked for over and over, and it hasn't been found. So nature is more clever than we are. We have to work harder. And working harder also puts more burden on the theorists to calculate things more precisely, because it looks like the deviations are going to be more subtle. Great question. Here's one down here.
Other than just like understanding the universe, is there any like use for this?
Yeah, that's a great question. Well, because we are working in a regime that is pretty far away from the kinds of things that do lead directly to practical devices. People had ideas for things that might have worked with muons. Muons live a long time. There was some hope, but this was a long time ago, that they might be used to catalyze nuclear fusion, which would allow you to get energy out. But it didn't work. So, for the most part, the way this kind of research benefits society is partly just from the understanding, and then partly from driving technology. So, in the 1980s, experimentalists were trying to communicate with each other, and they were already grouping into large collaborations around the world, and they needed to send each other pictures. So they devised something called HTML, and that was a language that is underneath every single web page. And it wasn't like it was done on purpose to invent the web, it just came out by accident. So we call that a spin-off. There's another kind of spin-off, which is a literal spin-off. When you take these electrons and bend them in a circle, you get radiation, X-rays, very intense X-rays, called synchrotron radiation. And that radiation can be used to study materials, can study proteins, for example. If you can crystallize a protein, then you can bombard it with X-rays, and you can make a pattern that tells you where the atoms are inside that biological molecule. And that can help you design drugs for various things. So that's another example of a spin-off. In fact, my laboratory, which was built as an electron laboratory to do fundamental collisions of particles, is now mostly what we call photon science. So it's mostly devoted to making these intense X-ray beams. There's a question back there.
I'm curious, what kind of software does your department use, and what are the current developments in that area?
So, most of the people at this conference use Mathematica. Have you ever heard of Mathematica? Who here has heard of Mathematica? Okay, that's pretty good. It wasn't just the ringers in the audience. Now I like to be odd, so I use Maple. How many people have heard of Maple? Well, still not bad. Okay. So those are, because a lot of us like to do things analytically. So we use this computer algebra where you can really see all the X's and Y's flying around. But sometimes then you need to do things really fast. And then you build a program in Fortran or C++, depending on how ancient you are and how much of a job prospect you want your students to have.
Could you elaborate a little bit on how they make the selection of those events to study and to keep?
Oh yeah, that's a great question. There is what's called a trigger menu. And it has it's like bigger than any restaurant you've ever been to. But everything is sort of grouped into objects at the LHC. An example of an easy thing to trigger on is what we call a muon. That was this heavier cousin of an electron. Because it's heavy and almost stable, it goes right through the detector and makes it to the very outer parts of the detector. So if you see tracks of ionization left in the outer part of the detector, and you can crudely, very fast, try to point them back, then that's called a muon candidate. And any reasonable looking muon they would trigger on, or high enough, energetic enough. That's just one example. And then jets. So jets are so copious that they cannot trigger on them at the same energy as a muon. You have to have way more energetic jets to trigger on. Then you have to develop more complex triggers, because the Higgs, it doesn't, well, in some of these modes, it makes some jets, but they're very wimpy jets. So you have to couple together the different items on the menu. You know, you have to take a muon at this energy and a jet at this energy. And so it's a huge fight, because the total amount of bandwidth is fixed. And so people are fighting for their physics by fighting for bandwidth in the trigger, because there are all these events that are getting lost, and the more you can get for the kind of experiment measurement you want to do, the better for your measurement.
You mentioned briefly about the WMAP and the early universe and the microwave background.
Yeah.
How can the Higgs boson affect our understanding and create new theories about the early universe and inflation?
Well, to be fair, it's probably mostly in a little indirect way. We just don't have many elementary scalar fields at our disposal, and the more we can understand about this one, where we can really get our hands on it, possibly the more we'll be able to say about the other ones. Like I said, there is one theory that the Higgs itself could be the inflaton, the particle that drives inflation. So we're sort of seeing it as a field around one part of, one part of its field value, but maybe it had a very different value in the early universe. But concretely, how you connect that to quantitative predictions, it's not completely clear.
Happy 4th of July. I've heard that there is going to be an expansion at the LHC, or at least it's being planned. How would that help in further, finding stuff?
Yeah. So, in general, the more collisions you have, the better. You can look for rarer processes that only show up when you get a much bigger data set. There are a number of different future plans. The most likely thing, which I think is maybe, very high likelihood of happening, is the high luminosity upgrade of the LHC. And that will, add to the amount of data. It will multiply it by maybe another factor of 20 from what we have now. And we already have about 30 from what we had at the time of the Higgs discovery. But that may not be enough to investigate the whole range of possibilities. So ideally, you would like to go to higher energy. That's actually easier on the detectors than going to higher luminosity, because it's such a ferocious data rate. Increasing it even more, this makes things incredibly difficult. But to go to higher energy, your only choice is to figure out how to build stronger magnets. And that's been quite difficult. Or you could go to higher energy by making a bigger ring. So there are plans to go to a possible 80 to 100 kilometer ring. So CERN has a direction called the FCC, or Future Circular Collider. It would probably be something like what happened in the 80s where they first put this machine called LEP in there that had electron-positron collisions. And then you can, in this case though, you could make the Higgs in a much cleaner environment. And in some sense, I think I have a quick backup slide on this. That is, this is roughly speaking how you find the Higgs boson at an electron-positron collider. And on the right is how you find the Higgs at the LHC. It's not very easy at the LHC or at a future proton collider. It can be done, but when you have an electron-positron collider, pretty much every time the Higgs shows up, you can find it. But, so those are some of the options for CERN's future. And other people around the world have other proposals. There's a proposal to build something called the International Linear Collider, and that is to make electron-positron collisions, but not in a ring, as a linear machine. There was a trial machine of that type that ran at SLAC in the 1990s, but this one would be, again, at an energy where you could make the Higgs boson and also do other kinds of measurements as well that are difficult at a proton collider. So those are the sort of main future steps. China has expressed some interest in possibly building something like the previous, what we were talking about earlier, a large circular machine. But none of these are definitely going to happen. We'll just have to see.
I think on that note of outlook, let's close. Let's thank Lance again for his presentation.